Welcome to the course on Foundations of Cognitive Robotics. I will first tell you about the course evaluation procedure. You will have a final exam which is optional, but with a fee you can actually go for this. E-certificate will be issued to only those who would register and write the final exam, provided average assignment score will be 25% of average of best 3 out of the total 4 assignments. Exam score will be 75% of the proctored certification exam score out of 100. Final score will be average assignment score and the exam score. However, it should be greater than or equals to 40 out of 100. Now, you will be eligible for an e-certificate only if average assignment score is greater than equal to 10 out of 25 and the exam score is greater than equal to 30 out of 75. If one of the above two criteria is not met, you will not get the e-certificate even if the final score is greater than equals to 40 out of 100. So having said the course evaluation procedure, let us start the course on cognitive robotics. I'll first talk about the reference books that I will be using in this course. The first important book is by Human Samani, which is published by Taylor and Francis. The title of the book is Cognitive Robotics. And then we also would follow the basics of neuroscience from a standard book like Dale Purvis, and Cognition, Brain and Consciousness, some introduction to cognitive neuroscience, by a beautiful book from Bernard J. Bars and Nicole M. Gage, which is from the academic press. And the other important book is from Rolf Pfeier of MIT Press and George Bongard, that is on how the body shapes the way we think, a new view of intelligence. And also you need some basic knowledge of control systems, particularly the modern control and AI based approaches. So you can follow books like the book of Jitendra Raul Ayagiri or other similar books in this direction. I will now tell you a little bit about the motivation beyond this subject of cognitive robotics. As you can understand that cognitive robotics is an interdisciplinary subject. So it draws inspirations from computer science, from psychology, and of course from robotics. And how this intermixing have created this new subject, cognitive robotics, the basic motivation of it, what do we have new in this particular course, I'll give you this basic introduction in the first lecture. The motivation behind this cognitive robotics would come from this very famous quote from Brazil, which is Felix qui potuit reram cognoscere causas, which means fortunate was able to know the cause of things. As Homo sapiens, you would little understand the significance that how fortunate we are, that we are able to know or we can pursue to know the cause of the things. Now, if you watch carefully that these to know something, in Latin it is called cognoscere, the root of the word of cognitive, which has in fact two parts in it, that cogn part of it, which is the learning or knowing, and the process of it. So cognitive referred to the process of knowing or learning something. In fact, till the mid 15th century, cognition usually would mean ability to comprehend, mental act or process of knowing. In 17th century, the meaning started to get extended to include the things like perception and sensation. Now, when we talk about cognitive robotics, what we mean by this? Well, cognitive robotics would actually mean, if we literally try to translate, would mean that how to create the thinking robots. Or if you try to, the word thinking may sound a little bit vague to you, so if you try to dilute it, it would mean how to endow intelligence to a robot. Now, while doing it, we would not only consider Homo sapiens. We would consider, in fact, that there is this process of thinking present even in animals. So, as a starting point, while developing the robotic information processing, we will consider that how this cognition can happen in animal and what are the interesting characteristics of that cognition that we can actually impart in robot. This is opposed to a more traditional artificial intelligence techniques. The other important aspect here is that when we say about the robotic cognitive capability, it is not only in terms of some sensing or some actuation. We aim to include characteristics like perception processing, attention allocation, anticipation, planning, and complex motor coordination, reasoning about other agents. Here this word agents would mean broadly about both living and non-living non-living, say, robots, and perhaps even about their own mental states. That's what is our objective, that can a robot comprehend about its own mental states, and can a robot have this kind of animal or human like capabilities of attentions, allocations, etc. So that's what is the goal. How can we develop such a thing in cognitive robotics? Now, I would just like to show you a small video. Many a times we think that intelligence is something which is only possible in higher order animals. I mean, mostly mammals, and even among the mammals, I would say primates and the Homo sapiens. But that may not be the case. Let's look into this simple example of a much lower order animal biologically, that's about an octopus, and let's see that how this octopus can have attention, can have perception about a problem, and can think about a strategy to escape. So you see, here is a bottle where we have kept an octopus, and you can see that I have taken it from a interesting YouTube link, and it is just the lid is closed, and you can see that the direction is showing that if there is a movement from these angles, as you can see already that movement is happening, the tentacles, the octopus is moving, it's further moving, it has understood that which direction it has to move, and it is doing some reverse direction also. So to understand that which way it has to apply the torque, and it has completely understood, it is applying it in the perfect way now. If you wait and see that how it is now going through this entire process of unlocking itself, it is fascinating. You can see that it's moving its limbs, and it knows that this unturning is over, so it can take the whole lid out, and you see it's taking out all its limbs and it's fascinatingly escaping. Can a strong AI robot, can it plan for such a fascinating escape? I will give you one more fascinating example. This time it's about the fish, and it's about the spawning of the fish eggs. This particular example I have taken from an Amazon rainforest. And just observe the amount of intelligence. In this case, there are two fishes, the male and female, which are cooperating with each other in order to make the spawning of the fish possible, not in water but outside the water. Let's look into that example. This will tell you that intelligence is not just the property of higher order animals. So this is Copella arnoldi, commonly known as splashing tetra, which lays its eggs outside of water. And the advantage of doing it is many, like the eggs can develop faster in outside water, where you are getting more oxygen supply, because many a times in such rainforests the oxygen demand, biological oxygen demand, will be quite low because of algae covers, etc. So that way it helps, and also it helps to avoid the predators. Now let's see, we know the advantage, how it is actually executing it. So you can see that in this water, these splashing tetras, the school of these splashing tetras, you can see both male and females. Now you will see that how this spawning is happening in them. So they are still inside water and then looking for a target. They have to jump out of water, so they are looking for a suitable target with the fisheye views. They are searching that which plant will be suitable for spawning, and after some movements in various directions, they have fixed the leaf. You can see both the male and the female are spawning their eggs. The male would remain for a little more time. They will go back. Some eggs you can see already. Again they will be back. They will be spawning the eggs, and you can see how they are actually spawning the eggs phase by phase. They are populating it on the leaves. So they have chosen the target, they have come out of water, and they have spawned the eggs all over the leaves. Now that's not all. A fish cannot live without water. The same thing is true for the eggs. You have to keep it moist at least. So what it is going to do is that it is going to precisely find out the position of these leaves, and you see how it is splashing water so that all these eggs would remain moist and they can nicely grow inside. You can see already the life has started. You can see these small the fishlets are actually inside. The moisture is helping them, and this male tetra is continuously moisturizing until these fishes are growing to the extent that with the help of further water they can start their journey back into the stream. So do we not call it as a good example of intelligence? But this is coming from fish, from a quite biologically lower order animal. So that is the basis when we say that when we talk about intelligence and when we are talking about imparting intelligence, it has to happen from the animal level itself. Now let us talk about some basic definitions of cognitive robotics that you will find in the open literature. The general perception of cognitive robotics is given very nicely by Human Samani, and he has said that you can consider it to be an approach of creating artificial intelligence in robots by enabling them to learn from and respond to real world situations. You are not pre-programming the robots that if this happens you react in this manner. You are giving it some clues that based on the real world situation how you can take your decision. So this is sometimes also called that how to interact with the unconstrained environment. And you need of course a suitable control architecture in order to interact with such unconstrained environment, acquire knowledge and use this experience for your further action. In other words, you should generate predictive capabilities to augment the immediate sensory motor experiences. So what kind of control structure can actually give us this? Well, one of our very famous control structure which was proposed by John Boyd, which is based on observe, orient, decide and act, in other words a OODA loop. If you look at these carefully, that there are these four sections: observe section, in which you are carrying out observations, unfolding the circumstances, check what is the information that is coming to you, and then take these informations, take it forward, do a feed forward and look at it from the prism of various, say, cultural traditions, various analysis and synthesis that is available with you, your previous experiences that you have understood, any new information, whether you are perceiving, whether if there is a genetic heritage of this kind of informations that you have already acquired. Based on these orientations, you feed yourself forward and you take certain decisions. Now, whatever decisions you take, you also feed them back in the observation process. Let's say you have taken a decision that the observation is more like a cultural observation. Then you modify your observation towards the cultural direction. Or you want to correlate it with your previous experiences. So you observe more, keeping your previous experiences in mind. And also, based on your decision, you feed it forward further and take some actions. Now, as soon as you are taking the actions, that also you have to feed it back so that you are having more unfolding of your interactions with the environment. As you are unfolding your interactions with the environment, you are learning more and you are getting newer observations and you are feeding it through this entire circuit. And during this process, particularly in the orientation phase, you continuously give the implicit guidance and control that are there based on the system you have. Now, these are some of the control architectures which can help you in an unconstrained environment. We will talk more about this type of control architecture in future. Now, there are three directions of development for the robot. The first question is that, can we consider this kind of cognitive robots as a quasi-person? Many people think that since these robots have a sort of intelligence, thinking process, perceptions, in other words, they operate in a manner which is identical to that of humans, so shouldn't they have some legal rights and shouldn't they have some duties? Even though in certain philosophies like Judeo-Christian philosophies, this kind of humanism outside the Homo sapiens, we call it transhumanism, is generally treated as a taboo, but certain other cultures like Japanese scientists, they are perfectly comfortable with the idea of robots as like living entities. You might be knowing that in Japan, the robots have participated even in social marriage. So this is a concept that is coming up, that with the increased level of intelligence, human-like properties like attentions, perceptions, etc., you may consider a robot to be a quasi-person. Some people are a little less optimistic. They are ready to consider it like a quasi-animal, and they consider that, well, we need to give an intelligence like animal. However, the robot must have an owner, and the owner will be held responsible in case of any accident or a mischief. Just like if you have a dog and this dog creates some problem, and it's the owner of the dog who is held responsible. Similarly, it's the owner of the robot who will be held responsible. Now, some more people think that it's neither an animal nor a person, but it is simply a product, and hence, just like for other products, the manufacturers are responsible. Similarly, for the robots, the manufacturer or the operator will be responsible. So there are these three different viewpoints towards the direction of the cognitive robot. I will now show you one example of one of the latest humanoid robots which has been developed by Honda. You will be knowing about the name of it, which is also called Asimo robot. Now look at this particular work which is reported by Honda very carefully, and think of it that in which category you can place this robot based on this action that you are going to see. You see the robot here, Asimo, is bringing something, looks like a flask which is having some drinks in it and a glass. Look how carefully it has come to the unconstrained environment without any human help, went to a proper position, and then without fouling, it has taken a sidewise movement and it is standing in front of the table that he has brought, the cart with the drinks that he has brought. Every time you will be now seeing this, you should also compare the performance of it with the octopus example that I have shown you. See, now it has hold, it now knows how to unscrew the bottle. It has processed the data, it's opening up the bottle perfectly, keeping in mind that it may have some fluid which should not spill out. So it's applying just a good amount of torque to open it up. It has opened up and kept the lid fast very safely, and then it has picked up that glass. Now it has to decide about the proper angle, proper orientation, and gradually fill the glass. That's what it has done with the help of its fingers and the visual scanning and the touch sensors and the actuators. So now that it has filled the glass, it is doing a social duty. So it has given this water or the drinks to a person. So based on these interactions, you have to tell me that in which class you will be keeping this Asimo robot. Would you like to give it a right just like a Homo sapiens, transhumanism, Or would you like to treat it like an animal? Suppose if it does anything wrong, suppose if it pours, spill off this fluid on the lady when it is serving, so would you hold the operator, the people who have actually developed the robot responsible, or you would held the person who has designed, who is actually running the robot, the operator, to be responsible? Or you would think, no, the robot is an autonomous on its own, so it has its own personality, so is the Asimo robot who himself or herself is responsible for the acts. So this, as the intelligence is propagating, as we are able to give more and more human-like behaviors into the robots, these are becoming important issues for us, very important legal issues. Now, as you can see that in the last example of the robot, there is some embodiment which has taken place in the robot. This word embodiment is very important because there was a group of people who are from the strong AI group, and for them the artificial intelligence does not necessarily require any hardware to be present. Let's say if there are a network of computers, according to the strong AI group, it can be an intelligent agent. But according to the embedded group, this embodiment is very, very important in order to impart intelligence to the system. So here the psychology and computer science people have to actually merge with the robotics branch in order to give this embodiment into the cognitive robots. Now there is a very famous scientist, Sarney, who has given a strong argument in favor of this type of embedded AIs, which is also known as weak AIs, and he has proposed a sort of a Chinese game in which he has considered that, let's say, there will be a person in the Sarney's Chinese game. He has considered that, let's say, there is a monolingual person who only knows English, and he is in a closed room, and you are supplying him with all the Chinese letters and some Chinese scripts and some instructions which tells that the syntax says that how each one of these letters are part of the script. Now, if he writes something based on these Chinese symbols in the form of a script, can we call him to be a Chinese writing person? If he speaks something based on such instructions, can we call him to be a Chinese speaking person? Because the person actually doesn't know anything about these symbols. He only knows that the syntaxes that is given to him. So the fallacy is that if you have a robot which is having these symbols as the first batch and these script as the second batch and these third batch as how to join them, the instruction set, based on that we cannot actually call that the robot has some kind of a Chinese personality, or similarly the robot is having intelligence. Today you have, for example, Alexas with us, very popular. Now can we call Alexa to be an intelligent being? Because in the back end it doesn't understand each one of the symbols with which it is trained. So the Sarney's weak AI logic is that in order to have intelligence, you need to explore with the environment. So you cannot really call this kind of instruction based intelligence to be a proper intelligence. you need embodiment in order to have intelligence. So if we look at Sarde's arguments, you can put it in a way that every organism with this intelligence should have a certain biological structure, and this structure under certain conditions is causally capable of producing perception, action, understanding, learning, and such other intentional phenomena. So this is the significance of embodiment in cognitive robotics. Now there are 5 such possible categories of embodiment. The first one is just simple structural coupling between agent and the environment. Well, when I told you, when I talk about agent, it can be any living or non-living thing which has the capability of interactions. So in this sense, if you consider Alexa, so there is a structural coupling between Alexa and the environment, because if the environment changes, you give some instructions, Alexa understands and it changes its behavior. So there is a structural coupling. There can be further improvement of structural coupling in terms of historical coupling. So you can improve your AI up to that level that you can keep track record of a history of agent environment interactions. So it can learn from it and it can adapt itself based on it. But with that Alexa example, there is no physical embodiment there. There is no body that is there. On the other hand, for the Asimo, there is a physical embodiment that is there. Now this physical embodiment can have a sort of a initial group of embodiment like organismoid embodiment, which is not exactly an organism but organism like bodily form, like the humanoid robot. So here the physical bodies have, at least to some degree, it has a similar form like an organism, and it has the sensory motor capacities with it. So that should be the starting point of the cognitive robots, and the ultimate point is like organismic embodiment, which is like autopiliotic. Autopiliotics are the systems which can self-create itself, which can maintain itself on its own, just like a living system. So that's the final goal of developing this kind of cognitive robots. But however, in order to have cognitions, you must have physical embodiment and it must have organismoid embodiment, and the final goal is to develop organismic embodiment. So this is what we will be pursuing in our course. That means these building blocks we will be discussing of the organismoid environment and how to develop it for cognitive robotics. Now for the cognitive robotics development, we will talk about 3 different types of strategies, like physical interaction of the robot. How can a robot develop complex coordinated movements while exploiting the basic dynamics of the system? The robot has to be aware of its basic dynamics. And then the social driving factors, and can a robot bootstrap itself and try to know on its own? And finally, all these 3 properties, how can you integrate them in order to get a kind of a complete system out of it, which is capable of having physical interactions, social interactions and developments. So this is what we will be exploring in the course as we will be having the future lectures in these directions. Thank you.